Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shaikh bin Azhar and my mention number is 223767. And today I will cover the topic about the second law of thermodynamics. This topic has made most of students confused. So for this discussion, we will make it as easy as possible. So the major statement of the second law of thermodynamics are the following. First, closest statement. It is impossible for any system in such a way that the sole result would be an energy transfer by heat from a cooler to hotter body. Second is Kelvin-Planck statement. It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surrounding while receiving energy by heat transfer from a single reservoir. The third statement is the entropy statement. It is impossible for any system to operate in a way that entropy is destroyed. So to make it easier, we make two easier statements that would help us more in understanding this law. So first is, let's call this as high to low. For any process, a natural flow will always be from higher energy value to lower energy value. For example, coffee, the temperature of coffee is higher than its cup. And as what it says, from higher energy value, so the temperature of the coffee gets transferred to the cup, which is cooler, lower energy value. And that's why the cup gets hotter. So now, let's move to the second one. Let's call this as perfect is impossible. For every real world process, there will always be losses. That means you cannot convert all of your car fuel into mechanical energy which can rotate your car wheel. Proof is the gases you see on the car muffler. Or try bouncing a ball by throwing it up to the air. See that as the number of bouncers increase, the level of bounce decrease because of the loss of energy which is transferred to the ground. So that's it. I hope this made it easier for you. Before we jump to the next subtopics, I would like to make a note that second law of thermodynamics is a law and it is applicable to everything in our world. So for the next thing, I will explain to you guys about thermal energy reservoir. Thermal energy reservoir? What is it? Well, a thermal energy reservoir is simply a humongous mass, and so it can then store a whole bunch of thermal energy. Because remember, thermal energy is equal to mass times specific heat. So when we talk about reservoir, we talk about something that can absorb a bunch of energy and still not change in temperature. Like, think about the ocean. If I pour my hot coffee in the ocean is not going to change temperature. Well, if it does, it's going to be so small that I won't even able to see it. And if it could, it will be very, very tiny, and so I can say effectively that my temperature of my ocean is constant. And that also means if I'm taking energy from the ocean, I can say it's at a constant temperature. And why do I care about this? It's make my equation a lot simpler. I don't have to worry about doing a whole bunch of integral, because the temperature changing as I pull heat out, that going to change a lot of our equation. We want things to be constant. So when we talk about energy being moved from one place to another, or energy coming in, we are talking about it coming from a reservoir. So it's always constant temperature. The amount of heat that can come from it can be constant too. So in real life, thermal energy reservoir that we use are the ocean, rivers, lakes. Like a nuclear power plant, they will not have an actual lakes that they are pouring into, but they have like some man-made lakes around them that they use it to dump the heat into. And same as for coal power plants, some power plants are right next to the river, and when they are breathing out smoke and producing power, they are dumping that hot water into the river. Fish don't like that, so if we can minimize the waste heat, it is a good thing for us to do. And finally, ocean is the biggest one for us. It's taken the burn of global warming because the extra heat in our atmosphere get absorbed into the ocean. And I mean, it is apparently like several nuclear bombs a second of energy being put into the ocean every single day. And the reason it doesn't change in temperature that quickly is because it is such a humongous mass. Okay, next, two things here: thermal energy source and thermal energy sinks. So reservoir can be those big things. We are getting energy from it. If I'm taking energy from it, it is a source. And if I'm giving energy to it, it's a sink. So for all of our problems, we are going to be thinking about this source and sinks. You'll see there are magical little bubbles. They are not magical bubbles, they are real things. It just, if I'm not caring about them, if I just know that heat coming from them or going to them, then I don't need to talk about their properties. Like, yes, thermal energy sinks usually atmosphere. Not always just depend what you are doing. Thermal energy source a lot of time combustions. As we are going forward to be running into those more talking about the combustion, talking about the atmosphere, talking about our effects on it. But for now, just know that we can say red bubble, grey bubble is a source, it's a sinks. One give me heat, one takes the extra heat away.
Hello, my name is Fidaus Al-Hakim bin Muhammad Idros and my metric number is 223070. I will be explaining about thermodynamic temperature scale. It is a scale that used to measure temperature that is independent from the properties of the substance. In the figure shown, it shows how Kelvin scale works. From a high temperature reservoir, or TH, when heat is absorbed by a system, which in this case either reversible heat engine or refrigerator, heat absorbed is considered as QH. And QL is the heat released by the system or in this case reversible heat engine or refrigerator to low temperature reservoir at TL. The formula given is QH over QL equal to TH over TL. For Kelvin scale, its unit is Kelvin. So in order to convert from Kelvin to Celsius, we need to minus Kelvin minus 273.15 to get in Celsius. And if you want to convert from Celsius to Kelvin, you just need to add your temperature in Celsius plus with 273.15.
Hello, my name is Muhammad Akif bin Norzaimi. My metric number is 225279, and now I'm going to talk about the Carnot heat engine. So, the Carnot heat engine is the hypothetical heat engine that operates on the reversible Carnot cycle. Now, let's look at Carnot efficiency. For any heat engine, the thermal efficiency is equal to 1 minus QL over QH, which QL is the heat of the low temperature reservoir and QH is the heat of the high temperature reservoir. But for Carnot heat engine, the thermal efficiency is 1 minus TL over TH, which is TL is the temperature of low temperature reservoir and TH is the temperature of high temperature reservoir, and they're both in Kelvin. Here we can see that when the thermal efficiency is less than the Carnot efficiency, it's going to be an irreversible heat engine. And when the Carnot efficiency is equal to the thermal efficiency, it's going to be a reversible heat engine. And when the thermal efficiency is more than the Carnot efficiency, it's an impossible heat engine because the heat engine cannot have more efficiency than the Carnot efficiency. Now, let's look at the quality of energy. So, as we can see from this diagram here, when the temperature is 925 Kelvin, the quality is going to be 67.2%. When the temperature is 500 Kelvin, the quality is 39.4%. From this, we can see that the higher the temperature is, the higher is the quality. Now, let's go to question 1. A Carnot heat engine operates with a source at 1000 Kelvin and a sink at 300 Kelvin. If the heat engine is supplied with heat at a rate of 800 kJ per minute, determine A, the thermal efficiency, and B, the power output of this heat engine. Now, let's look at the solution. So, we get the TH is equal to 1000 Kelvin and TL equals to 300 Kelvin. The heat we get is 800 kJ per minute. We convert the minute into hour, so then we get 13.33 kJ per hour. So for question A, the NTH ref is equal to 1 minus TL over TH. Substitute TL and TH, we get 1 minus 300 over 1000, and then we have 1 minus 0.3, and it's equal to 0.7, and now NTH ref is equal to 70%. For B, the power is equal to NTH.ref times the Q. So we get 0.7 times 13.33 kJ per hour, and then we get 9.33 kilowatt.
For question 2, it stated that a Carnot heat engine receives 650 kJ of heat from a source of unknown temperature and rejects 250 kJ of it to a sink at 24 Celsius. Determine the temperature of the source and the thermal efficiency of the heat engine. By that statement, we know that QH is 650 kJ and QL is 250 kJ, and it gives us TL also, but in Celsius, so we need to convert it in Kelvin, which is 297.115 Kelvin. So in order to find TH, we use formula QH over QL equal to TH over TL, and we just substitute the value that is given, and we will get 772.59 Kelvin. Or in Celsius, we get 499.44 Celsius. For the thermal efficiency, we use N equal to 1 minus TL over TH, and we just substitute the value that we get, and we will get 0.6153 or 61.53% of the efficiency.
So that's all from us. Thank you for watching.